All right, integration by parts, the final battle. So we're going to go over some sort of tricky ones, or at least tricky looking ones right now. This one right here, it seems like almost every class covers it, where you've got two things, neither of which would go away as you take derivatives. Because if you recall in the previous videos, or at least in the first one, we always did stuff like x squared times sine x, or we did the integral of x cubed times e to the x. And whenever we did those, I said, hey, make this your u, because as you keep doing the integration by parts once or twice or three times, you'll keep knocking down your exponent by 1. So if you make this your u on the first round, then your u on the second round will just be x without the x squared. Or if we made x cubed our u in this case, then on the first round of integration by parts, then we'd end up with an integral that had x squared in it, make that our u again, then we get down to an x, do it again, get down to 0. So the strategy, when you have something that does go away with derivatives against something that doesn't, you just made your u equal to the x squared term. But what about this guy? We've got something that never goes away multiplied by something that never goes away. That is a problem and a dilemma. And I'm going to show you how there's a really magical trick, but you just got to keep your eyes open. If this is a situation, we'll do integration by parts twice, and then some really tricky algebra, and everything will work out, but you got to spot it on the test. Now, a lot of students do that problem. Even if it's a slightly easier one semester class, good chance you'll see this particular type of problem on there where they mess with you and give you two things, with this complicated setup. Arctangent, I don't know, I just don't see it very often, but we'll take a look at that as well. Also, we'll take a look at a couple of problems which look like they'd be crazy, but are in fact just U sub or even just barely need U sub for them. All right, so first things first, because this is the one that's most common, here's what's going to happen. We're going to have to make u equal to something that doesn't go away. So we're going to set this equal to, we'll make our u equal the first one, because why not? E to 2x, and make our dv the rest of it, sine x dx. And our du is going to be 2 e to 2x dx, and our v is going to be equal to negative cosine x. Alright, so no big deal so far. So just plug and chug as usual, uv. So that's going to be, looks like negative e to 2x cosine x minus the integral of v, which is negative cosine x, times du, which is 2 e to 2x dx. Alright, so as you can see, we did make a lot of progress here, because we've still got, just like in the original, we had a sine, a trig function times an e to the something. And this one, same story, e to the something times a trig function. So we didn't actually make any progress, and it might look like we're spinning our wheels. But it turns out if we do trig sub one more time, everything will come full circle, and we'll be okay. All right, so I'm going to end up recopying down here, but for a second, let's just pick our u and our du. Once again, I would say, hey, you know what? Or actually, let's just rewrite this real quick. Plus, we can bring that 2 out front. I like my e to 2x in before the cosine, not sure why. Just make it look more like the original problem, put things in the same order. Alright, so at this point I'm going to pick my u to be e to 2x once again, which I know seems like a waste of time, but you'll see it's not in a second. And cosine x is going to be my dv. So my du is going to equal 2e to 2x, and v is going to be equal to sine x. Alright, and there's a dx here. Alright, so now if I plug and chug through the formula once again, first of all, don't want to forget this term. It'd be a shame if we forgot that term. Now I'm just going to, so then we had a plus 2 times this whole integral, and that's what I'm going to replace with the uv formula up here. So u is e to 2x times v sine x minus the integral of v, which is sine x, times du, which is 2e 2x dx. All right, now here's where it looks particularly futile to to be using integration by parts. Because you'll notice that the integral we still have here, we haven't made any progress. We still have a trig function times an exponential. So we haven't knocked anything down or reduced it in any way by doing integration by parts twice. And what's worse is we actually have the same problem we started with. So if I'm just going to rewrite this to show you just how bad it is. So we got plus 2. I'll distribute in this 2. Why not? So plus 2 e to the 2x sine x minus, and then I've got 2, because I'm distributing, so I did 2 and distributed that in, so I got minus 2 times this 2, so that's minus 4 times the integral of sine, oops, I might want to put the e in front, e to the 2x sine x dx. Alright, so this looks horribly futile, because I was trying to find this integral, e to the 2x sine x, and I've still got e to the 2x sine x. It's like the original problem is in the answer. That's crazy. So it seems like we just totally wasted our time. Except check this out. On the left side, I still have the same stuff I started with, right? Integral of e to the 2x sine x dx. So this integral. So think of this as a variable. If I've got one of these on the left, and I've got negative 4 of them on the right, couldn't I just combine like terms? So if I want to get rid of negative 4 of something on the right, don't I just have to add 4 times that same thing? So I'm just going to add to both sides of the equation. I'm going to add 4 times the integral of e to the 2x sine x dx. And of course, if I'm adding it to the right, I have to add it to the left. So I got to add 4 times the integral of e to the 2x sine x dx. So once I do that, I get that 5 times the integral of e to 2x sine x equals, so that cancels that, and on the right side I now just have e to the 2x cosine x plus 2e to the 2x sine x. Alright, you might still be thinking we're spinning our wheels, but we're really close. Because what they asked us for was, hey, what's the integral of this thing? Right now, though, I just found out what's 5 times the integral of that thing. So basically, right now I've got 5 times the answer, but I really just want the answer. So I just need to divide both sides by 5. So the trick was that just because you go in circles, it's not all bad. Usually this type of problem, it involves a sine or cosine. So basically, if you start with a sine, you have to do integration by parts twice in order to come back around to sine. Same thing, if we started with cosine, we would have taken integration by parts twice to get back to cosine. So this step where we figured out, you know what? We have the same integral on the right as we have on the left. Let's combine like terms. That magic always happens after doing integration by parts twice. I don't think I've ever seen a problem that did it after 3 times or after 1 time. It's always after doing it twice, because it always involves sine or cosine. Nice thing about sine and cosine, if you're trying to cook up a problem like this, is that they just alternate, right? Take the derivative of sine, it's cosine. Take the derivative of cosine, it's sine. Just keep alternating one and one, again and again. So that's why doing the opposite, or doing it twice, ends up looping you back around to the original, so you can combine like terms. Pretty crazy. All right, here's another one that looks crazy. Now you might be thinking, hey, Chris, you just did an example where we had something that, 2 things that basically are not polynomials. 2 things that don't go away as you take the derivative. So you might be thinking, hey, I'm going to make one of these my u and the other one my dv and work it from there. There's actually a much more simple problem than that. I just need to combine powers because these are like bases, so I just need to add the exponents. So this is e to the x plus 3 dx. Pretty sweet. So that's just going to be e to the x plus 3 plus c. Oh my gosh, did I forget plus c in that last problem? That'd be terrible. All right, so plus c. And now we didn't have a u sub problem because our u was just x plus 3, which means our du was just dx. Since there was just a 1 in front of x, that's why I didn't have to worry about u substitution. All right, here's another one that looks pretty nasty. Looks like we might have to make secant our u and tangent our dv, or vice versa. But really, secant tangent is just a derivative of secant. So the integral of secant tangent is secant. Nice. So again, once you've learned all these fancy techniques, like integration by parts, and it goes on from here, everything starts looking like a scary problem at that point. Anytime you see two things multiplied together, you'll start thinking, hey, that's an integration by parts problem. But that's what the teacher is going to use against you. Some of these really are legit integral formulas that are very straightforward if you just forget about integration by parts for a second and just think to yourself, hey, how would I, would I have been able to integrate this without integration by parts? And that's the first step in every one of these problems, is to take a look and say, hey, could we integrate this without integration by parts? And that is the first step that is going to save you a lot of time and trouble and points. Just like adding a plus c to everything, you always want to try u sub before you try anything else. All right, here's kind of a tricky one. We are going to need u sub, so this is not a fake out this time. But it's kind of interesting that we only have one function here. In all the other integration by parts problems, we have had two things multiplied together. It's kind of like the product rule. But for this one, we don't know the integral of arctangent, so I don't want to make that my dv. Because dv, you have to integrate to get v, right? So I got to make arctangent my u. But then you might be thinking, well, hey, what's our dv going to be? Because we just used everything for our u. Well, we didn't actually. We have not used the dx yet. And that's kind of an unusual thing. It kind of looks funny. But sometimes your dv is just going to be dx. And that's pretty simple because the integral of v is just x. And the integral of dx is just x. So that's easy. And then arctangent is something that we know how to take the derivative of. It's kind of a funky formula. Using the chain rule, it'd be u prime over 1 plus u squared. But since we just have an x here, our du is going to equal 1 over 1 plus x squared dx. All right, so at this point, we can plug and chug. U arctan x times v, which is just x, minus the integral of v, which is x, times du, which is 1 over 1 plus x squared dx. Huh. That's weird. Let's think for a second now. Hey, wait a minute. Is it possible that this is a u sub problem at this point? This guy right here. Because if I made my u the downstairs, just make the denominator of the fraction u, then the du would have an x in it, right? So it turns out I need this x to be my du. So I've got an x. I just need another 2 in front of it. So I need a 2, and therefore a 1/2 out front to compensate for the 2. So at that point, I've just got x arctan of x minus 1/2 times the integral of du over u. And what is the integral of du over u? Natural log. So we got x arctan x minus 1/2 ln of u, which was 1 plus x squared, and of course plus c. Don't want to forget your plus c. All right, pretty fun stuff. As you can see, these get tricky. That loop-to-loop thing, when in doubt, I mean, just you almost want to memorize that one problem, the one where you have the e to the x sine x. That's always going to be one where you have to do it twice and then combine like terms. Take that integral term from the right side, recognize that it's the same integral as you have on the left side, and just